Welcome back to our course in Algorithms and Data Structures. As you know, this is a part of a wider group of courses that aims at teaching from very basic Python programming to the analysis of drone acquired images using computer vision and deep learning. And at this point, we are in the second part of our second course in data structures and complexity. And of course, the second part is the complexity part. In the first unit in this part, we spoke about basic concepts in algorithm complexity, which basically meant what algorithm complexity means for us. And basically that was that we are going to consider the complexity of an algorithm thinking about how the time it takes to compute the algorithm changes when the size of data processed by the algorithm grows. In the first unit of the course, of the complexity part of the course, we saw two examples of algorithms, of groups of algorithms which we call complexity classes. The first group was O of n, or linear complexity algorithms. And here we saw, for example, that searching in a list or traversing a list, doing something like computing the average of the list, is a linear complexity algorithm. So when the size of the data processed by the algorithm grows, the time it takes to compute the algorithm also grows, but it grows following a linear tendency, following a line. We also saw a second complexity class, which is called constant complexity. And an example of that was accessing a list. That means that even when the size of data grows, in this case, even when we have a longer list, accessing one particular position of the list, it always takes the same time, regardless of how big the data being processed is. Those algorithms that basically do not grow their time when the size of data involved grows are called constant time algorithms. In this second session, we are going to be looking at how we go about computing the complexity class that one algorithm belongs to, how we go about describing the behavior that the time it takes to compute the algorithm has when the size of data grows. And we will begin with some practical matters like the fact that constants, even additive or even multiplicative constants, do not matter when computing the complexity class of an algorithm. And here I have some examples that I recommend that you have a look at, but I'm going to comment on this, having a look at this particular cell of a Jupyter notebook. And here, using matplotlib and numpy, I have drawn basically four functions, n, 5n, 3n plus 5, and n log n plus 2 log n, okay? Which you can see here in their formulas. And my point is that all of these tendencies that I have not derived from any algorithm here, but that algorithms could follow, basically all belong to O of n. So if I have an algorithm whose time is exactly n seconds when I have n size data, this is a linear algorithm, or O of n algorithm. And if I have one that's not n, n is the green one, not n, but 5n, that's also a linear type of complexity. You can see intuitively that the behavior is always the same. All these algorithms have a computation time that grows linearly when the size of data, the n, grows. They just happen to follow different lines, but they all follow lines. So this is the definition of my complexity class. And here what we can see is that if I add 5, what I do is that I'm lifting my line up. But when I go to infinity, when the size of data grows, this is not going to matter anymore. I'm going to start a little bit higher up, but I'm going to have the same tendency. This is not going to affect my tendency. Not only that, the multiplicative constants also do not matter. If I'm just multiplying by a constant, the tendency, the degree of the polynomial, the general asymptotic behavior of my function is not changing. Okay, it's growing following a line. We will see later that we will have quadratic and cubic algorithms. In all of them, the complexity class that each algorithm belongs to is not affected by either additive or multiplicative constants. Not only that, but lower order functions, for example, we will see later what logarithmic complexity means, but let me just tell you that that's smaller than linear complexity. It grows smaller than linear complexity. That doesn't make the complexity of a linear algorithm change. The higher order term in the computation of the time of the algorithm is the one that dominates. So we can ignore constants, but we can also ignore lower order terms in the asymptotic complexity of algorithms. If you remember your probably high school classes about how to draw functions and think about how the limits and the asymptotic behavior of functions was computed, you might remember that lower degree terms are often ignored.